Yes, thank you, Veronika. Thank you for the talk also. So now we have our last speaker for today. So I'm really happy to introduce Ira Ktena. Ira is a senior researcher at DeepMind, working on deep learning research for life sciences. Previously, she was a machine learning researcher at Twitter, where she carried out research at the intersection of recommender systems and algorithmic transparency. She completed a PhD in medical image computing at Imperial College London with Professor Daniel Ruckert, and her research focused on developing methods for modeling and analyzing graph structure neuroimaging data at an individual or population level. Today, Ira will present her work about exploring fairness in transductive settings for neuroimaging studies. So Ira, the floor is yours. Thank you for joining us.
Yeah, it's a pleasure to be here, and thanks a lot for the introduction, Enzo. Yeah, I've heard all the talks today were super interesting. So yeah, I hope the audience is not is still excited about the topic, given that it's the last one. So hopefully you can also see my slides now. Perfect.
Yes.
Okay. So yeah, just a very brief motivation into why we're looking at the transductive setting, and I guess for most of my PhD, I was working with graph data. I was looking at brain connectomics, and the reason for that was, first of all, because cognition is a network phenomenon, but also, most importantly, because for certain disorders, neurodevelopmental and neuropsychiatric, there's not only changes in the wiring or the strength of the functional or structural connections, but there may not be a physical trace in standard kind of structural imaging. And there is a standard pipeline on the right-hand side that shows how we get from the structural and functional imaging information, including structural MRI, diffusion-weighted imaging, EEG or fMRI recordings of neurophysiological signals, to a network representation of the brain. But I won't get into too much detail, given that the focus today is a bit different. So a couple of years back, actually together with Enzo, we started looking at the ABIDE dataset, which is essentially a multi-site study that essentially compiled together imaging and other information for neurodiverse and neurotypical individuals. As you can see, it's a list of 20 different sites. And first of all, what we observe is that the representation of the sites is pretty skewed. So the largest site contributed more than 170 participants' data, while the smallest data set was in the order of tens. And so this is clearly an issue, and I think it was highlighted by other speakers earlier, how important the scanner type is, and whether we, when we look at this kind of multi-site setting and then we only observe certain subgroups in certain sites, how that can be problematic and challenging for our modeling endeavors. So how prior studies looked into this multi-site setting is they had two setups. One was called the intra-site cross-validation setup, where a certain percentage of each site was kept for training, and the remaining percentage was maintained for testing. So both at training and test time, we would see a certain percentage of all the sites. While in the inter-site setting, we would have a held out site. So this would kind of measure the generalization capabilities of a developed model that has been trained only on the remaining sites, but the held one, the one that is held out. And what we observed when we started working with this data was that if we looked at, so here I'm plotting pairwise distances between the connectomes of individuals that have received the same diagnosis, so in blue and orange. And then in green, we have the pairwise distances between connectomes that have received a different diagnosis. So if we look within a single site, site 1 and site 2, then we see that the distances for different diagnoses were higher compared to the distances between individual connectomes with the same diagnosis. But as soon as we put everything together and we looked at the intersite setting, then this differences almost vanished. So of course, that highlighted how different the sites or the impact of the scanners and the differences across sites that can emerge. And what we wanted to do was to kind of leverage this information that accompanies our imaging data, and that includes acquisition site or other phenotypic information that was relevant to the condition that was in focus, and to leverage that in a kind of population setting. So along with collaborators at Imperial College, we came up with this population graph that would then capture on the nodes the imaging feature vectors of all participants in our database. And then on the edges, it would capture the pairwise similarities that would emerge from the auxiliary information, and that included phenotypic imaging and genetic information, depending on the condition. So genetic information was only relevant to Alzheimer's disease, and we looked at also the autism spectrum disorder application. And so, yeah, that population graph would be fed to a set of graph convolutional layers that would give rise then to our predictions for the unlabeled nodes only. So this is just like a bit of background for our setup. This is the only reason I'm mentioning this. And then we looked at what is the effect of the population graph structure itself. And what we called back then the phenotypic graph was the graph that relied on this kind of auxiliary information that was available for the participants in our database, whereas all the other graph structures were not using this information. And we could see that that was actually quite helpful for the metric that we were looking at for neurotypical versus neurodiverse classification. And then when we looked at further into the graph structure and what specific attributes are helpful for classification, then at the top of the list, we saw that sex and site information was particularly helpful to incorporate into the graph structure in order to get more accurate predictions. Now, in terms of the follow-up work, what we didn't do at that stage was to really understand what was the impact of relying on the sensitive attributes for our graph structure. And in a follow-up study that started in collaboration with different universities, the Alan Turing Institute, University of Queensland, EPFL, and University of Southampton. And I think Fernanda should also be on the audience. So she kind of led this research. We started looking at fairness considerations in this transductive setting, which was quite different to the other setups that have been described today or are more prevalent in literature. But first of all, I didn't include definitions of fairness and different pre-processing and in-processing techniques, given that these were covered in the introduction as well as later on. But just to recap, this is like a very nice and comprehensive kind of diagram of where biases can creep in at different stages of care. So during model development and model deployment, as well as in the interaction with clinicians, there's different kinds of biases that can emerge. And we can have, so if we imagine that each row in this matrix corresponds to an individual, and then each column is a feature, then if we're missing a whole set of features, for all the individuals, this can be considered cohort bias, but we might also be missing data only for individuals from a certain protected group, in which case we have this minority bias. I think other speakers also talked about label bias and other issues that can emerge during model deployment that have to do with shift of the data and how that is impacted by putting the model into production, and essentially the model seeing data that it hasn't been trained on, and but also patients not having access to a particular model, in which case we have a privilege bias emerging. A kind of story that we often see in machine learning in general, but in particular in machine learning for health, is this kind of debate between data and algorithms. After quite often we have fixed our data set, and then we're trying to make our algorithms as fair as possible. And then from the algorithm development side, we might have we might think that we've come up with the most fair algorithm that we can, but then we need to make our data fair. And in reality, there needs to be a synergy between the two, and there are biases that can creep in both of those. So now getting back to this Abai data set and the multi-site setting, if we look at the 8 largest sites that participated in the study, for 2 of them, we had no female participants. As you can see here, there's only male neurodiverse and male neurotypical participants coming from these 2 sites, which is of course very problematic, both in terms of training, but also if we try to evaluate the fairness of our models for these sites, given that we have no observations at all. And another thing to note is this interesting study by people at Google Brain and collaborators that looked at fairness in different domains. So they looked at 2 applications. They looked at dermatology and also EHR data. And they looked at whether ensuring fairness in a source domain guarantees fairness in a new target domain. And the conclusion that they reached was that it's actually not the case. So fairness essentially doesn't transfer. So it wouldn't be enough then to estimate fairness in the most prevalent sites in our database. And this is something like worth considering also in other settings where we're trying to evaluate the fairness of our data set or our models. So for example, for different age groups, they observed kind of subgroup performance that was on par across the 4 different age groups. But then in the new unseen target domain, there was a clear gap between the youngest and the oldest populations. So this is a setting that I described earlier, and essentially the answer that we're trying to the question that we're asking and that we're trying to get an answer for was whether relying on sensitive attributes or the kinds of attributes that we rely on, how does that impact the performance gap between the subgroups of interest. So we looked at the sensitive attributes that we use to kind of define our subgroups was sex. So first of all, we considered the effect of the pre-processing strategy, as Andy mentioned earlier, that has to do with how we choose our training data. And essentially that boils down to the stratification strategy that we use in this setting. So in order to make the different stratification strategies comparable, we had to keep a held out test set that was the same across those strategies, because otherwise our test set was always kind of changing, and then that would make results not really comparable. So what we did is, first of all, we randomly selected 10% of individuals as a held out test set, and included 2 males and 2 female participants, one from each diagnostic label, into our test set. And then for the remaining sets, we performed cross-validation, where we had 10 different random states and 10 different model seeds. So overall, we had 100 models that we evaluated. And what we saw was that results were quite similar, regardless of the stratification strategy. But what we observed was that actually relying on sex and site information in comparison to the baseline that didn't use a population graph was actually reducing the difference in true positive rates. So then zooming into this stratification strategy, then we wanted to see what is the impact of the graph structure. And what we saw was, so here the stratification strategy is fixed. So we're looking at sex and site, site and diagnosis stratification. So, and then we changed the graph structure and performed 10-fold cross-validation. So in this case, our test set is not fixed anymore. And again, we have 10 different model seeds as well. So again, we have 100 models that we are evaluating. And what we observed, both in terms of area under curve and in terms of differences in true positive rates, was that the sex graph was actually reducing the gap between or incorporating the sex into the graph structure was reducing the gap between the 2 subgroups. So overall, what we observed was that, first of all, the stratification strategy was not important or didn't have a significant effect on the fairness metrics that we considered and that we thought were most relevant to our application. So this result might come as a surprise, given how much the composition of the training set has been highlighted in different settings. But it's worth noting that this is a transductive setting. So we do observe the features of all participants in the database and only the labels of our training data. So this is quite different to the inductive setting, in which we don't have access to the features from the evaluation set, for example. And another encouraging result was that the higher performance of graph neural networks did not come at the cost of higher true positive rate difference. So quite often an easy way to trick, let's say, fairness metrics is to reduce performance across the board. And we observed that this was not the case, and the model that would rely on the sensitive attribute in the graph structure was fair and was actually more accurate across the board. So these results align with prior literature around fairness through awareness. So essentially saying that discarding the sensitive attribute is not the solution, and leveraging it can be beneficial for fair predictions. So overall, the graph structure itself was more important than the composition of the training set, again, in the transductive setting. In terms of ways we try to address and bring this gap even closer to zero, we tried clustering twice, or fine-tuning on the underrepresented groups, but those only marginally improved fairness in the setting. And I guess our results in terms of the graph structure can also be kind of supported by literature in the space of autism spectrum disorder, which have identified different patterns of functional connectivity in individuals in male and female individuals with ASD, and hint that different latent representations can be beneficial for the two subgroups. Some limitations of the study. First of all, reducing identity to binary or categorical feature attributes. So we did try to find data for non-binary individuals, and we only found a reference that was kind of claiming describing the need for it, but there was no data available. So this is in general, I guess it links to the second point of really reducing our fairness analysis to some elements of identity that we perceive and that we consider fixed. And these are often like social constructs that vary depending on the context. So this is something that Maria de Ortega and her work has highlighted in different contexts of machine learning. And it's very important to understand that a measured construct might not be necessarily a relevant construct. And if we always evaluate against the former, then our results can be misleading. So even in terms of ethnicity or skin type, this can change depending on the context for a single individual. So it's worth keeping this in mind when we do these kinds of analysis. So maybe that gives a bit of a gloomy picture, but I think the future is looking actually quite promising in terms of solutions or things that can be done to improve fairness of models applied in the healthcare domain. So one important aspect is doing thorough dataset reviews. I think this was again mentioned earlier, and I'm just sharing here two studies that looked at ophthalmology imaging and skin cancer image data sets. And these are kind of widely used data sets, and then really understanding where those images come from and which parts of the population they are capturing and representing is very important to raise awareness and to understand the limitations of these data sets and the algorithms that are developed on these. Along the same lines, I think there's a lot of improvements to come from participatory AI, and datadiversity.org website that the standards standing together consortium put together is kind of a step in this direction. So the goal of the Standing Together initiative is to define best practices for health data sets, to also map dataset deficiencies in priority disease areas, while at the same time identifying barriers to implementing those standards across the world. So one very interesting component of this group is the patient and public involvement. So they're running these eDelphi studies that allow essentially individuals from minoritized groups to answer questions that are posed by the research team. And there's also a public involvement engagement subcommittee that is helping them answer moral and ethical issues around data collection. And this is, I think, a very nice initiative to that starts to highlight how important it is to really involve patients and more widely users of AI algorithms into their design. And there's this study from Abeba Birhain and other people at Google and DeepMind that looked at opportunities and challenges for participatory AI. So I think this is like a very interesting future direction. in a different kind of line of research, then we have privacy enhancing technologies. So there was a study that was published at Nature Machine Intelligence a couple of years ago that looked at secure and private AI and how that can be used to essentially train models on data that we never see. So privacy enhancing technologies have advanced a lot, and they can protect patient data from theft or attacks or adversarial manipulation. And at the same time, they can help us, such technologies can really open up access to much, much more diverse and representative data sets of the population without compromising like a patient's privacy. So I think this is like a potentially very promising direction. And if you hear a talk by the founder of OpenMind, then you can really see that this is one of the main motivations of coming up with tools like PySift and so on. And some companies out there like Twitter in a different setting, and Microsoft as well, they have started kind of partnering with OpenMind in this scenario and started like testing these privacy enhancing technologies in order to understand the impact of algorithms on different aspects of our lives. So I think that this will only grow in the future, and I'm very excited to see this actually being used with hospital data. And more from the moving away from the data aspect and back to the model aspect, there's been this interesting study on shortcut learning. So what they looked at is whether essentially they can estimate whether a model is unfair based on whether it's kind of using shortcuts, and by looking at this causal relationships between the image, the condition or label that we're trying to predict, and the sensitive attributes. They essentially say that if the model is kind of unintentionally using the sensitive attribute to make a prediction, then it's using this shortcut and it's not capturing information in the image that is relevant to the disease. So this is kind of an interesting way of basically diagnosing our models and understanding when they are relying on information that is kind of spuriously correlated with the label. So to conclude, I think that we should really consider AI systems as kind of another human almost in the loop, in the sense that they can also be biased, they can be wrong sometimes, but a human expert is also likely to be wrong, and we need to factor that in. We shouldn't go to the extremes of being like too averse of like using this technology or relying 100% on it without really understanding when it can be wrong and why. So and apart from that, we need most importantly, we need representative data and better data. And we need algorithms and models that don't rely on shortcuts for the predictions. And yeah, that's all for me. So let me know if you have any questions.
Amazing talk, Ira. Thank you very much. I think it was a great way of like a great last talk, because you also opened many directions with your last slides, showing future directions that are worth exploring in this field. I have some questions, but also there are questions here. One from Melanie. So she says, thanks for this great talk, Ira. It's great how much you have focused on the dataset composition. In your talk, you have focused on ABIDE, one of the large neuroimaging datasets. Now they are starting to collect even larger datasets. For example, the HBCD. Could you comment on the value of trying to address recruiting issues in terms of representation at the site level, or if this is even possible, especially with respect to attributes not being easy to capture? Do we need to value this more than trying to fix the issues arising in the machine learning afterwards? Well, I think this is a complex question, but Ira, if you have any thoughts.
Yeah, I think this is a very it's a very good question, and I think it's hard to answer, in a couple of minutes. There's a lot there to unpack. I think it's important to explore both. First of all, I guess the question has to do also like with disparities to access, and maybe how do we capture all the information about our data and our participants that will be relevant to kind of evaluate then model performance in subgroups of interest and what that really means. I guess in terms of recruiting, I remember seeing this study actually that would basically make it harder, I think, for mothers, for example, to participate in the study because of the time of the day that the study had to be carried out, or if there's like financial incentives sometimes to participate. I guess these also always like play a role, and especially in the medical setting, and depending on where the study is based, I guess also the health insurance can have an impact and so on. So I think there's like guidelines, and Karim, if I'm not mistaken, kind of talked about what are good standards for creating like new data sets and so on. But I think this should be explored, or this should be pursued in parallel with trying to make machine learning models more fair. But yeah, it's important to keep in mind what are the relevant, let's say, dimensions that we want to explore. It's important to keep in mind intersectionality. So because there's a lot, when we look at intersectionality, then we end up with very small groups. And there are some other challenges that emerge there. But yeah, I think they can be explored in parallel, actually.
Yeah, totally. Well, if people have other questions, they can also post it in the chat. I'm really interested in this work because I mean the transductive setting is a particular setting, right? So it's like different to other. I think this is why it's also really relevant, the work you have been doing in this particular paper. But related to the particular study, you were showing somehow that this fairness through awareness is somehow helping in this case, right? And whenever I look at fairness through awareness, and particularly in cases like gender, for example, where we have these categories, you were saying, these are social constructs sometimes, and we cannot create labels for every possible gender, or things like that. And so when we think about fairness through awareness, we need these labels somehow to tell the model. So I think this is a really interesting like problem, or I don't know even how to address that with these categories. Any thoughts you want to share in that direction? I mean, or maybe you have thought about that before, and yeah. I don't know, it's something that I always wonder, how to address this problem. Maybe discovering these groups, this is something we're also starting to explore, like maybe discovering which are the attributes or the categories that are generating subgroups where the model is unfair. I don't know, maybe you can comment on
that. I think, yeah, it's a tough one. And I think that we should look at it as a limitation rather than basically we should have this disclaimer that we're making this assumption that we can kind of rely on these labels, but they're actually nowhere near like a ground truth, if that makes sense. But it's some tool that allows us essentially to understand what kind of basically how our algorithms can affect different subgroups, but it's not a perfect way, and that it needs improvement. So I think there's a lot more people that are working like in ethics have thought about this a lot more, and how you deal with kind of identities that are kind of unobserved in a way, and how you study them and how you capture them and how you try to incorporate in a maybe more quantitative analysis. But I think this is only kind of this has started to grow only very recently, so I think it hasn't yet translated into more kind of technical domains. It's still more in the socio-technical space, but I think there's a lot to learn from those studies.
Yeah, amazing. Yeah, I remember the paper by Shakir Mohammed actually on fairness of unobserved characteristics. This is really interesting. And also people are now pointing to other resources from ICML and other conferences on unsupervised debiasing that may be a direction worth exploring in the future. I think it's a really hot topic. Yeah, right.
That's a very good point.
Well, Ira, thank you very much for this last talk. I will now hand it over to Ben, who will moderate this panel. So people, yeah, Ben, you go ahead and you